All right. Hi, I'm Magdalena, and I will be talking about vectored space models and about causality between levels of abstraction, which is the project that I've been working on during the PIBBSS program. The general research question I've been asking is, how can we model causality between levels of abstraction? So I think of levels, like we might model systems at different levels of abstraction. So we might go very detailed and look at quantum fields, and we might be a bit more abstract, be at the level of cells or at the relatively abstract level of individuals, or even more abstract organizations in society. And at all of each of these levels, we have properties that are interesting, and it makes sense to talk about them. And when we model causality, we can model causality within a level quite well. Like, we have good tools for that. But as soon as there's causality between levels, or when it's unclear what the level even is, we don't really have great tools. And one approach to think about this kind of thing are vectored space models. And this is what this talk is about. As an overview, I'll start by talking about the motivation, like why I even care about causality and abstraction, and how tools we have are incomplete. Then I give an introduction in the framework and some structures that are built upon this framework. Some results that we have, the so-called semi-graphoid axioms, how we can construct a vectored space model from a graph, and our main result, which is the soundness and completeness theorem. And then in the conclusion, I'll say what I think is great and not great about vectored space models and give a summary. So for context, we're writing this paper. This is an extended abstract of this paper. It only has 4 pages. And if you have access to the slides, you can just click on this link and find it there. It is published at the Iliad conference. And we are also working on a longer version. So to the motivation, why do I care? Some assumptions when talking about causality and abstractions. When we're asking this question, how do we make AI safe? This is a very confusing question in general. And the first assumption is it's useful to understand, like, in order to answer this question, it's useful to understand how minds work in general, both in a descriptive and a prescriptive way, like how should minds work. And then the second assumption is that causal models and abstractions are both very important puzzle pieces when we try to figure this out. So the main motivation of all of this is to have a good framework to think about causality and abstraction, and then hopefully be less confused about how minds work in general. So when we think of causality at different levels of abstraction, the existing models that we have is that if we are within a level, we can talk very well about causality. There's a very rich literature based on causal graphs. Judea Pearl won a Turing Award, and there's, based on his work, there's this whole field of causality with like really useful tools for modeling independence and intervention and counterfactuals and lots of things. And between levels, when we're talking about abstraction, that's something like an individual might be made up of cells, and there's a deterministic function between these levels of abstraction, like, or not always, but often there can be deterministic functions. For example, if we have a thought, this is like completely determined by the underlying patterns of neurons that are firing, and those in turn are completely determined by the underlying quantum fields. So deterministic functions are just a normal thing that appears when we think of different levels of abstraction. And we can also think of properties at the abstract level as a summary of properties at the more detailed level. So for existing models, we have causality within a level and abstraction between levels. But these models are limited because we can also have causality between levels, for example, like the actions of an individual can totally have a causal effect on the whole organization. So there might be causality here. Or we might have something like abstraction within a level when we have self-referential systems. Like, for example, a thought can be a summary of all the thoughts I have. Like when I think a lot about causality, then this is a summary of all the thoughts I have. And then the question is, do we maybe need a separate level for meta thoughts? Or maybe if I think thoughts like I think a lot about thinking about causality, maybe we should have another level for that. And at this point, it kind of becomes unclear what levels even are, or if this is even the right model to think about it in terms of levels. And then you might be asking, okay, but what's the problem? Why can't we just put everything in one big causal graph, have all the variables there? That seems simpler than thinking about different levels of abstraction, right? But we can't do this. There are at least two problems. One problem is that we get causal cycles from the micro level to the macro level. What that means is like causality, like a causal arrow means that if we intervene on one variable, then the other variable that is downstream of it also changes. And in this case, if we intervene on micro level variables, for example, if I intervene on all the atoms in this pen and move them all a bit to the right, then the macro level variables of where the pen is will also change. But also in the other direction, if I like intervene on the macro level variable of moving the pen, then this implicitly means we also intervene on all the atoms in the pen. But in like the common models for causal graphs, interventions are usually just modeled as acyclic. And so we would only have, like we would kind of put the macro and micro into one single variable so that we avoid these cycles. But then we aren't actually modeling different levels of abstraction, but just like within a level. So if we are only working within one level of abstraction, this is not a problem because we don't have these micro and macro in the same causal graph. We just have different causal graphs. But the point was that why we can't have like one big causal graph, right? So yeah, this is a problem. And then another problem is that deseparation becomes incomplete. Deseparation is a criterion for independence, which is defined on graphs. And as soon as we have deterministic functions, like if some variable being a deterministic function of another, like the like abstraction, this becomes incomplete. I have an example in the next few slides for that. And factored space models address this part, but they don't address this part yet. But this part is always present when this part is present, not the other way around. So in some sense, it seems likely that having addressed this part is like a step in the direction of also addressing this part. But this is like an open question. Maybe it's not actually, like factored space models might not actually be useful for solving this part of the problem. All right. How deseparation is incomplete. Deseparation is a graphical criterion for independence, and how it's defined is that there is no deconnection. A deconnection between two nodes A and B is a path between A and B without colliders, and a path doesn't have to be a directed path. Like you can walk along the arrows in both directions. So for example, if you have a treatment and it makes people recover more quickly, but also has a side effect that people sweat more, and maybe the weather is also influencing the sweating, then there is a deconnection between sweating and recovery, because there's a path and there's no collider on the path. And that makes sense because these are actually dependent. Like if you know that someone is sweating, it's actually more likely that they will be recovering. And but the weather and the recovery are independent, and there's also no deconnection between them because this path has a collider in it and the collider blocks this deconnection. So yeah, these are deseparated and independent. And then there's also a conditional deconnection, which is a bit more complicated, but the important thing is it's a property of a graph and it captures the property of the distribution, which is independence. And you can think of it as if you condition on something in the middle, you block the path. It's like the simplest version of this. But yeah, it has a lot more detail. And we say a graph is a perfect map of a distribution. And that usually means it's kind of the right graph for this situation if deseparation and independence is equivalent. So if the nodes A and B are deseparated in the graph given C, then this independence formula also holds for the distribution over A, B, and C. But the problem is that if we have variables at different levels of abstraction, then there is no perfect map. And an example of this is, say we have a vector valued random variable, which is called x, which has it's just a tuple of multiple different random variables. And then we have its mean, which you can think of as a summary statistic, and a variable that depends on the mean, which is, for example, just z equal to y plus some independent noise n. And if we model this with different graphs, we have like the detailed level graph, where we have the detailed level variable x that causes z, and the abstract level where we have like the mean that causes z. And then there's deterministic functions from the detailed level to the abstract level. Here it's just the identity, and here's like the mean function. And then here we have like a probabilistic function where n is some noise. And as a reminder, independence, A and B are independent given C, means that when we know C, then A has no information about B, and also the other way around. So what that comes down to here is we have like Z is not dependent of both X and Y together, because if we know both X and Y, this does give us information about Z. But as soon as we know Y, like given Y, Z and X are independent, because Z only depends on X through Y. There's no other part of X except the mean that somehow influences Z. But we also have that if we have X given, like the detailed variables, then Z and Y are independent, because if we have X given, then we already know everything there is to know about Y. Like if we have X, then we also have the mean of X. So Z can't tell us anything about Y anymore. And we might think maybe we can just like take this graph and say, okay, we have like X, then we take the mean and then we add some noise. It seems reasonable, but this is not a perfect map, because like a perfect map would mean that these independencies are all deseparations in this graph. But X does not deseparate Y from Z. So if for deseparating y from z, it would need to be kind of in the middle between y and z. And but since both y needs to deseparate the other two and x needs to deseparate the other two, we can't have them both in the middle, right? So there's no perfect map. And there's this axiom which tells us that there just is no graph that has these deseparation. It's called intersection axiom. So the question is, how do we model this kind of situation? And now enter factored space models. Factored space models, the idea is that we have a factored space, which is a finite sample space called omega expressed as a Cartesian product. So what does this mean? Omega is the set of all these purple dots, and it's expressed as this direction times this direction times this direction. And so if we have like one particular item of omega, like lowercase omega, it's a tuple of the three directions. It's a bit like a vector space. And in general, a sample space is a space of the thing like that we have a probability distribution over. So if we have each of these dots is associated with a number from 0 to 1, which is the probability. And we say that a distribution factorizes over omega if for each of these probability, they are equal to the product over all the single probabilities of these individual items. And for comparison, there's also a similar concept of a distribution factorizing over a graph, which is a bit more complicated, but similar. And a random variable, just in general, is a function from a sample space to a value space. So when we write val of x, this just means all the values that x can take. So this is just a set that x maps to, like the codomain. And then a factored space model of a distribution. Like we start with a distribution over an observation space, and a factored space model is a factored space together with observation variables, such that the distribution factorizes and the observation variables, their value space is the observation space. And then a factor is just the projection, like it's a function from omega to omega I. And the projection meaning, like, for example, if we are here, then the projection to the factor 1 would be going, like, would map all of these in the same plane, would be mapped to the lowercase omega 3 here. So all of these would kind of be projected onto this axis here. And when, yeah, and that's why it makes sense to like think of the U1, U2, U3 like as these axes for this space. And whenever P factorizes, that's equivalent to saying that the variables UI are independent. All right, this was a kind of abstract, but let's go with an example. So the same example we had before, the detailed level X and then the summary, the mean Y, and like some that Z that depends only on Y, plus some noise. And to make this more concrete, say we have the value space of X is just 0, 0, 0, 1, 1, 0, 1, 1, 1. Like we just have two X's and they only take two values, and value space of N 0 and 0.5. Then the factors are U1 is X and U2 is N, because X and N are independent, because N was like independent noise. And also x together with n cover the whole space of outcomes. Like if we have x and we have n, then we know all the values for x, y, and z. So this means omega is the Cartesian product of the value spaces, and the variables are functions. So what this looks like is we have two axes, one is x and one is n. And here's like the value space of x with 0, 0, 0, 1, 1, 0, 1, 1, value space of n with 0 and 0.5. And then the omega is the set of these dots, like all possible outcomes. And then each of the outcomes is associated with a value for y and 1 for z. So for example, if we are here, x is 1, 0, then the average of 1, 0 is 0.5. And then the noise is 0.5. So 0.5 plus 0.5 is z, which is z equals 1. So we are here. And now we have this, we can define the history, which can be thought of as a set of sources for a variable. So the history of a variable a is the set of indices of the factors ui we need to determine the variable a. So we can kind of think of it as a computation history. And for example, here, the history of x would be 1 because x is equal to u1, so we only need u1 to know x. So 1 is the only item in, like the only element of the history of x. And then there's more examples we can look at later if you're interested in the details. And then we also define the conditional history of b given a equals lowercase a, which are the indices that we need to determine b when we already know that a equals lowercase a. Plus the factors which are made dependent by conditioning on this a equals a. So the factors on which a equals a is not rectangular. I have the precise definition here, but it's easier with an example, I think. So for example, if we condition on z equals 1, this thing, that's not rectangular. And what that means is that it makes x and n dependent of each other. So for example, if we know that x is 1, 1, then we also know that n must be 0 in this, if you already know that z equals 1. So this means x and n are dependent. So u1 and u2, like 1 and 2 need to either both or none need to be in the history. And since the history of y contains 1, it also needs to contain 2, because 1 and 2 are made dependent by this z equals 1. And then I have more examples that you can look at later if you want to have all the details. And now we can define structure independence. So structure independence, A and B are structurally independent in omega when the histories are disjoint. And that's the same, we use the same symbol as statistical independence because these are very related, as we have a theorem later. So I just copied these from last slide. And for example, if you look at x and n, history of x is 1, history of n is 2. There's a disjoint, like they are not overlapping, so x and n are structurally independent. And then have some more examples again. And then we have conditional structural independence. So A and B are structurally independent given C when their conditional history never overlaps for any lowercase c that C can take. So for example, if we look at like y as the C here, if we look at the history of z given y equals y, no matter what y is, this history only contains 2. And then if we look at the history of x given y, This is either 1 or it's empty. So in no case does it overlap with 2. So these are structurally independent given y. And then we have more examples again. And what is interesting about this list is that the fourth one and the A and B one are exactly the ones that we weren't able to model with a graph. So this thing, like this factored space model, is a perfect map for the distribution that we have, while there is no perfect map that is a graph. So my claim is that structural independence on factored spaces is better than deseparation for representing independence. Okay, now to the results. I'll start with the semi-graphoid axioms. There are these axioms. They're called graphoid axioms, a bit simplified version, but they get the gist. So for example, A and B, if A is independent of B, then B is independent of A. Like a lot of these kind of properties that an independence relation should have. And if a relation, like this relation satisfies all these axioms, then we call it a graphoid. And the blue ones are semi-graphoid. So if if a relation satisfies these 4, then we call it a semi-graphoid. And statistical independence, that's defined on a probability distribution, is a semi-graphoid. And only if we assume that all probabilities are non-zero, then the intersection axiom also holds and it becomes a graphoid. But usually we don't want to assume this because it's actually constraining us to have probabilities that are non-zero. And deseparation, which is defined on a directed acyclic graph, is a graphoid, and that's also where the name graphoid comes from. And structural independence, which is defined on a factored space, is a semi-graphoid. Like it only satisfies these 4. And that's a good thing because we want to allow 0 probabilities. And so it would be bad if the intersection axiom was satisfied. All right, now I want to talk about how to construct a factored space model from a causal graph. So what we do is we have a factor for each node and each configuration of parents. And this factor has as its content the value space of X. And for the root node that, if there's a root node that doesn't have parents, the only parent configuration is the empty configuration. So for example, if we have this graph and a value space of X, which is X1, X2, and value space of Y, which is X1, X2, Y1, Y2, Y3, then we have 3 factors. The values, like the one for X, where the value space of X is here, and then 2 for Y with the value space of Y here. And for this one, we have the empty parent configuration because X doesn't have parents. And for Y, we have the possible values of X as the parent configuration, which is X equals X1 and X equals X2. And so the factored space model looks like this, where we have these 3 directions, 1, 2, 3 factors, 3 directions, and the variable X is just going upwards, like X1 is everything here, X2 is everything here. And now what the colors mean is what the variable Y is in this model. So we have if X equals X1, so we are in this lower plane, then this is the direction that's relevant because X equals X1 is like this part. So Y is Y1, Y2, Y3 goes like in this direction. But if X equals X2, then this factor is relevant for Y. And Y is like Y1, Y2, Y3 goes in this direction. And when we look at the histories here, what we see is that the histories of x and y are not disjoint, which is good because x and y should be dependent. And we see that the history of x is a strict subset of the history of y, which is also makes sense because x is kind of before y. There's more subtleties to this, but yeah, for this presentation. And what this factored space model does is it represents the dependence relation between x and y, but also of any functions of x and y. So for example, if we had another variable that would be x equals x1 and y equals y1, this is just another variable in the sense of it's a function from the space to some value space, and therefore we can, it has a history, and we can, like, all of these things are defined on Z as well. Whereas it would not be clear where we could add Z into this graph. Then we have some theorems about constructed factored space models. The first is that if that deseparation and structural independence are equivalent in the MG is the factored space model that is constructed from G. Then the ancestor relationship is equivalent to the history being a strict subset in MG. And the distribution factorize, or a distribution factorizes, this is equivalent to MG being a factored space model of the distribution. And these are all kind of theorems that tell us that the construction is the right construction because it captures the things that we want. And then we have an expressivity theorem, which is when there is a graph, which is a perfect map of a distribution, then there is a factored space model, namely the factored space model MG, which is also a perfect map of the distribution. Wherein perfect map, in this case, like for a graph, means deseparation and independence are equivalent, and for a factored space model, it means structural independence and independence are equivalent. But this does not hold in the other direction. So we don't have a construction from factored space model to a graph. And in fact, like we saw in our example, we might have the situation where we have a factored space model that's a perfect map, but a graph, like there's no graph that's a perfect map. So in that sense, factored space models are stronger than graphs. Now we get to our key result, the soundness and completeness theorem. So first I want to state the soundness and completeness of deseparation, which is like a pretty important theorem for graphical models. It states that when x and y are deseparated given z in a graph, this is true if and only if for all probability distributions that factorize over the graph, x and y are independent given z in this distribution. And the result that we have is x and y are structurally independent in a factored space if and only if for all distributions that factorize over the factored space, x and y are independent given z in this distribution. And this looks very similar, right? It's just like replace deseparated with structural independence and graph with factored space. But actually, this is quite a bit stronger, and it's a generalization of this theorem. Because like if we construct the factored space model from the graph, then this theorem directly implies this theorem. But in general, here in this theorem, x, y, and z have to be nodes in a graph. Whereas here, x, y, and z can be all possible variables over a sample space. So for example, if omega is constructed from the graph, then this holds for all the nodes, but it also holds for all the functions of variables, which are variables in their own right. So this means they can be at different levels of abstraction, and some things can be functions of other things, and this theorem still holds. So that's why this is pretty strong. All right. So I'll get to the conclusion. First, what I think is not great about factored space models. I think one issue is that they're pretty complicated, which often is a sign that maybe the formalism isn't right. But on the other hand, in some sense, it's simpler than causal graphs. Like, in some sense, factored space models are just choosing the variables in such a way that the graph becomes the simplest possible graph, which has no errors. But it still makes it really hard to visualize. And I think this hard to visualize makes it a less useful tool. Then an issue is it still doesn't solve this problem of causal cycles that I talked about in the beginning, like the micro to macro thing. And we don't have a notion of intervention, which we do have in graphs. And intervention, like the notion of an intervention relies on the assumption that there is a graph. And so if we have less, like if we don't make this assumption, which in some sense we can't make, then we lose this notion of intervention. And I think this is a really promising direction for future work, that to find how we might model intervention in factored space models, like which assumptions we need to reintroduce in order to define interventions. And yeah, in general, intervention means setting the mechanism of a variable to a constant. But it's unclear what a mechanism would be in a factored space model and when it even should be defined, because some interventions actually shouldn't be defined. And this should ideally both match our intuition and coincide with interventions in graphs. So then what's great about factored space models, in my opinion, one is that it seems very natural, and just seems wrong that we can't describe independence if some variable is a deterministic function of another variable. Like, this shouldn't be the case. And yeah, it seems natural that we should be able to do this. And then in some ways, factored space models are simpler in the sense of the mathematical object is a set of axes, and the distribution factorizes if the P of omega is the product of P of omega I. And the mathematical object of a graph is a set of nodes and a set of directed edges, and the distribution factorizes if the distribution for one assignment of values is the product over all the conditional probabilities of the parent. And this mathematical object is kind of more complicated than this mathematical object, but this mathematical object is easier to visualize. So I think that makes it, in some sense, easier to work with. They seem very elegant. So the fact that everything is modeled in one unified structure and there's no privileged variables seems very nice and right to me. And that also means that we can capture independence between all variables at any level of abstraction. And we're making less assumptions. So we allow deterministic functions, and also the soundness and completeness of deseparation, which is like this pretty important theorem. We have like factored space models satisfy a more general version of this, which I think is a really good sign. All right, so I get to the summary. My motivation was we want to understand minds, and understanding causality and abstraction seems useful for that. In existing models, we usually think of causality within a level of abstraction, but as soon as we have causality between levels, or when it's unclear what the levels are, we need better models. And in graphs, we have that deseparation and independence are equivalent, but not when variables are deterministic functions of variables. For example, abstractions, like between levels. And then what we do is we move to a different mathematical foundation of factored space models, where we have that structural independence and independence are equivalent. And this is also true for deterministic functions of variables. For example, abstractions. So we can model independence between levels of abstraction. All right. Thanks.